this with matrices. Yeah, we didn't get to the attendance pick yet. I see this. I see there was people asking about that. So let's take a look at scaling now and see if we can map this thing into a matrix. I'm going to answer this question. I see one question in chat about scaling around a certain point because I want to use this picture that we had before. It's the same principle as we did with rotation. If I want to scale around this point, if I just scale here, my box is going to move in and out from the origin because each one of the vertices is going to get scaled in its location. So if I want to have the effect of scaling around this, I got to move to the origin, scale, and then move back. Okay, scaling for using matrices. So for each of our vertices, what we want is we want the point to go to some, so in this case, I've got it drawn with a 1, 1, and we're going to go to this point, RS. So this is basically the new x prime, right? This is the new point, is equal to r times x and s times y. So if we set up a matrix that looks like this, then we can write this as a matrix operation. And you'll see eventually why we want to write this as a matrix operation. So far, it's probably just, I'm just saying that we should, but you'll see the advantage of this coming up. If we write our point as a vector, so these are usually column vectors and placed on the right side of the matrix. If we make this multiplication, then just matrix multiply makes it come out to be this formula. So we can write things like this to get scaling. Translation, similarly, we can write some sort of matrix form of this, although it has a slightly different form. So we want our x, y position to move to some new x prime, y prime, and it's going to be shifted over by delta x, delta y. So these formulas probably make sense, right? X prime is x plus delta x. If we want to write this in some sort of matrix form, we can write it this way, where we have our point vector plus our delta gives us our new position. And this is a different form than the previous one. And that's because this is not a linear operation in x and y. It's an affine operation. And we'll see what that means in a little bit. For rotation, here's the formulas I was looking for earlier. So for rotation, if we have some point, and we want to find out where is it going to go, this position 1, 0 is going to go to position cosine theta, sine theta. And this Greek symbol here is meant to be the radius, right? So the new, if this is where we were, this is the position of x and y, can be written this way in polar coordinates. We're going to add some angle to that, and that is going to be our new points. Now, I've forgotten my trigonometry identities, but if you remember them, the trigonometry identity for this, you can rewrite this thing as this here. And why would we want to do that? Because now our new points are linear in terms of x and y. If we know what the theta is, this turns into a constant, right? If I want to rotate by 30, this is some number. Cosine of 30 is some number. So we can write those numbers into this matrix. And when we multiply this matrix, we're going to get x times cosine theta minus y sine theta, right? We get back exactly this formula. So the rotation matrix is exactly what this formula is. So if you're comfortable with matrices, then this should all seem very obvious. If it's been a little while since you thought about it, how we're getting from these formulas to these matrices may take you a little bit. This is where I had my additional slide to try to say something additional about rotation. I think I'm going to skip this one and I'm going to show this picture because this helps me. So why is the rotation matrix is cosine theta, negative sine theta, cosine theta. So the rotation, because if we think about a point which started at x1, y0, it's going to rotate by theta and it's going to end up at this position, which is, right, you probably remember this from your trigonometry, right? This is sine theta, this is cosine theta. So our position is going to move. So if we had x in some position, we want it to get to here. So if we had an x1, y0 matrix here that we were going to multiply, this 1, 0 would get multiplied, and we would get back exactly what we wanted to get to get our output position to be cosine theta, sine theta, right? The ones are going to pick up this column. So our output column is going to be cosine theta, sine theta. Similarly, if we started over here on y1, we're going to pick up this column negative sine theta, cosine theta to get to our new position. I don't know if it helps you, but anyway, I put a couple of different slides in this deck so that you can look at it later. That'll help you think about how did we get to this rotation matrix. It's not just a matrix matrix. There's an intuition that goes with why is it there. Shear matrix, I don't have memorized, and you won't have to use it. It's not one of the basic operations, but I think it's useful to see some examples of what can you do with shear. So this is if we put a matrix that has this kind of form, it's going to have this kind of effect on the vertices of the object. You can build shear matrices out of scales and rotates, or you can just write them down. In the assignment you're going to do, and in most of graphics, we use rotate, translate, scale. Shear is used less commonly. So here's our fundamental transformations. We have translation, which has this addition, and we have scaling and rotation, which are multiplies by matrices. So these are linear operations in our point. This is an affine operation. And we now come to a little bit of problem. If we'd like to compose all these things, what can we do? So let's say we had an object, and we want to translate it, then rotate it, then translate it, then scale it. So what is that going to look like? We have our point. We're going to do plus translation, and then we apply our rotate, and then we plus some other translation, and then we apply our scale. This formula is getting messy. It's not very compressible. If I have a stack of 100 operations, I have to keep track of what's going on in here. It'll be very difficult to use. So we'd like to play some kind of trick to be able to clean this up. What we wish is that we had matrices so that I take my point, I multiply times the translate, multiply times the rotate, multiply times the translate, multiply times the scale to get all of these things. And you might think, do you have to still store all this? But because these matrix operations have associative property, you can pre-multiply all of this and just be left with a matrix M. So you could have 100 or 1,000 operations, take all this, compress it down into one matrix M that you have to store. So this would be very convenient if we could make this true. Unfortunately, we have this additive property. So what to do?